When power system disturbances occur such as faults, line switching, or sudden load changes, power swings may develop. If these swings become too large, generators can lose synchronism with one another. Out-of-step OOS protection was developed to detect these conditions rapidly and take appropriate action to separate asynchronous areas. Modern advancements have improved the accuracy and speed of OOS detection and the coordination of protective schemes, ultimately enhancing system security and reliability. The United States power grid has experienced several major disturbances in recent years, including the massive blackout on August 14, 2003, and significant events in 1996 that affected millions of customers. These events typically occurred when the grid was heavily loaded, and multiple outages happened in rapid succession, causing oscillations between neighboring utilities, voltage drops, and eventually instabilities in both voltage and phase angles. Fully designing a system to prevent such rare, simultaneous outages is prohibitively expensive, so utilities implement special protection systems (SPS) and remedial action schemes, such as under-frequency under-voltage load shedding and controlled tripping of loads or generation, to reduce the impact of disturbances. Out-of-step protection for generators gained attention after major blackouts, including the 1965 Northeast power failure and the 2003 blackout. In response, industry groups developed guidelines and technical standards for setting OOS relays to ensure system stability. OOS occurs when a generator loses synchronism with the power system due to disturbances or malfunctions in its automatic voltage regulator (AVR). This condition can lead to high peak currents, mechanical stresses, and pulsating torques, potentially requiring the generator's separation from the system via out-of-step tripping relays. If the disturbance is mild, the system stabilizes with oscillations in the generator's load angle. Power swing blocking PSB relays are used to prevent unnecessary tripping during stable power swings, ensuring unaffected generators and transmission lines remain connected. During normal operation, a generator maintains a constant speed because the electrical torque it produces balances the mechanical torque applied to its rotor. When a fault reduces the transmitted power, the resulting drop in electrical torque while the mechanical power remains unchanged causes the rotor to accelerate. Consider a two-source power system initially at a balance point angle transferring power. After a fault, the output drops to PF, leading to rotor acceleration and an increase in delta. When the fault is cleared at delta C, the now higher electrical power output PC creates a decelerating torque because PC exceeds P0. However, due to the rotor's inertia, the angle continues to rise to delta F, where the energy gain during acceleration exactly matches the energy loss during deceleration, a condition known as the equal area criterion. If delta F stays below a specific limit delta L, the system is transiently stable and with sufficient damping will eventually return to its original balance at delta 0. But if delta F exceeds delta L, the decelerating energy is insufficient to counter the ongoing mechanical input, and the rotor continues to accelerate uncontrollably. This results in a loss of synchronism, meaning one part of the system rotates at a different speed than the other, leading to transient instability. Power system stability means that after a disturbance, be it a fault, load change, or generator disconnection, the system can return to a stable operating condition. The system's integrity is maintained if only the faulty parts are isolated, while the remainder continues to operate normally. In cases where generators or system areas lose synchronism, it becomes crucial to immediately separate those zones to prevent widespread outages and equipment damage. One effective mitigation strategy is controlled islanding, achieved through two complementary out-of-step protection schemes. Out-of-step tripping, this targets predetermined network locations to disconnect system areas that are experiencing unstable power swings, thereby preventing further outages. Out-of-step blocking, this scheme ensures that distance relays or similar protective devices do not operate incorrectly during power swings, restricting separation actions only to the desired locations. When disturbances hit a power system, their impact depends on both the system's current operating condition and the disturbance's intensity. A fault on a critical component once isolated by protective relays leads to fluctuations in power flows, bus voltages, and generator rotor speeds. These fluctuations trigger responses from voltage regulators and speed governors in the system. Based on the disturbance's severity and how the system's protective measures react, the system might either settle into a new equilibrium, a stable power swing, or become transiently unstable. In the unstable scenario, substantial differences in generator rotor angles occur along with large swings in power flow and significant voltage and current fluctuations, ultimately causing generators or interconnected systems to lose synchronism. When two areas of a power system lose synchronism, the entire network experiences extreme variations. In phase operation results in high voltages and low currents, while a 180-degree phase difference produces low voltages and high currents, leading to severe system disturbances. The principles behind these schemes and examines the performance requirements for distance relays during out-of-step conditions, highlighting challenges such as defending against unbalanced external faults and ensuring that only the affected phase is tripped during a fault, rather than all phases. Under normal, steady-state conditions, all synchronous generators in a power system operate near their nominal frequency, balancing mechanical torque with their electrical output. If disturbed, differences in generator speeds result in changes to rotor angles. Initially, the system self-corrects by shifting loads between generators. However, if the angular difference becomes too large, power transfer decreases, which can lead to sustained instability. Loss of synchronism, or an out-of-step condition, impacts transmission line relays differently. Some relay systems like segregated line differential relays remain unresponsive during these events, while others such as overcurrent, directional overcurrent, and distance relays may react to changes in voltage, current, and phase angle relationships. In some cases, these relays might even trigger during stable power swings from which the system can ultimately recover. For example, instantaneous phase overcurrent relays will activate if the line current during a swing surpasses their minimum threshold. Similarly, directional instantaneous overcurrent relays will operate if both the current and the phase relationships align appropriately, whereas time overcurrent relays typically remain inactive, though their response depends on current magnitude and delay settings. Phase distance relays work by measuring the positive sequence impedance for faults of value that varies with the phase angle separation between system sources during an out-of-step event. These relays will engage if the swing causes the impedance locus to enter their operating characteristic. Zone 1 elements, without any time delay, are especially sensitive, and Zone 2 elements in pilot relaying schemes are also prone to activation. Conversely, backup zone elements, owing to their time delays, often do not operate during swings. The operation of distance relays during power swings hinges critically on the interplay between the relay's polarizing memory and the measured voltages and currents. Modern microprocessor-based distance relays that include frequency tracking are less affected by polarization memory rotation. Additionally, if the line's positive sequence impedance is high relative to the system's impedance, these relays may operate during swings even during conditions from which the system could otherwise stabilize. Some out-of-step tripping OST relays provide only tripping functionality, while others also include power swing blocking PSB capability. The standard method for detecting an out-of-step condition involves analyzing the apparent impedance at the generator terminals. Transient stability studies help determine whether a generator will maintain synchronism under different contingencies. During an OOS event between a generator and the system or another generator, impedance shifts based on voltage and angular differences. When the systems are in phase zero angle difference, generator terminal voltage is at its peak, and current is minimal. Conversely, when the systems are fully out of phase 180 degree apart, voltage drops to a minimum while current reaches a maximum. Protective devices monitor these variations to detect OOS conditions. Out-of-step protection distinguishes between faults and power swings by monitoring how quickly the system's voltage, current, and impedance change. In a fault such as a short circuit, the apparent positive sequence impedance shifts almost instantaneously in milliseconds, whereas during a power swing the change is gradual. For example, a 180 swing at about 1 Hz takes roughly 0.5 seconds. Because both faults and power swings can cause the measured impedance to fall within the operating range of a distance relay element, the key lies in tracking the rate at which this impedance changes. Practical implementations use two impedance measurement boundaries with an integrated timing mechanism. If the impedance remains between these limits for a set period, the system declares an OOS condition and sends a block signal to prevent distance relay elements from operating. Various geometric forms like double blinders or concentric polygons are used for these boundaries, carefully positioned such that the inner boundary lies outside the largest protection region and the outer boundary is sufficiently removed from heavy load areas to avoid false triggers. Out-of-step protection serves two primary functions. The first is tripping protection, which differentiates between stable and unstable power swings and initiates network sectionalizing islanding to isolate unstable areas, thereby maintaining a balance between load and generation in each island. The second is the blocking function, which prevents relay elements from tripping during normal or stable power swings while allowing operation during genuine fault conditions. To ensure effective system control, these protective schemes are typically applied at critical network locations, often near the electrical center, with additional measures such as transfer tripping schemes used to manage separation in specific scenarios. Notably, OS tripping is designed to avoid triggering when the phase angle nears 180, as this could impose harmful stresses on circuit breakers. This approach effectively minimizes cascading outages, limits load loss, and preserves service continuity while protecting equipment during both transient and unstable conditions. Turbine control mechanisms, such as power load unbalance protections, can activate during system disturbances or load rejection events, but these should not be mistaken for an OOS event. Overspeed typically occurs after pole slipping, whereas an undetected OOS condition can eventually lead to overspeed. This makes dedicated OOS protection relays essential. The boundary between a stable and unstable response, known as the critical clearing angle delta C, is a key parameter for relay settings. Although a common reference value is delta C equal 120 degrees, comprehensive stability studies are required to determine the actual threshold. These studies evaluate system behavior by increasing fault clearing times until instability occurs, identifying both the critical angle and relevant swing rates. As power system oscillations occur, relays measure apparent impedance variations over time. Improper settings can result in misoperations of protection elements. These impedance changes are best illustrated using a simplified model of two generators, where the receiving end voltage ER lags the sending end voltage ES by an angle delta S, influencing system stability. Two stability concepts are central here: small disturbance stability, steady state. This refers to the system's ability to handle minor load or configuration changes over a span of 10 to 20 seconds. Transient stability, large disturbance. This addresses the grid's ability to maintain synchronism for a few seconds, typically 3 to 5 seconds, following severe disturbances like faults or sudden load changes, which can cause significant swings in rotor angles and power flows. Power system stability refers to the ability of a power network to regain equilibrium after experiencing disturbances. Under normal operating conditions, all generators work in synchronism, maintaining a balance between input mechanical power and electrical output. Stability studies are typically classified into small signal or steady state stability, concerned with the recovery from minor load variations and control actions over tens of seconds. Transient large disturbance stability, focused on the system's response during severe, fast-acting events like faults, which usually require analysis within a few seconds. A stable system will experience oscillations that eventually damp out. An unstable system, however, will see increasing oscillations that lead to loss of synchronism. Here, E sending and E receiving are the sending and receiving end voltage magnitudes, X is the total reactance, and delta is the phase angle difference. The corresponding power angle curve shows that as delta increases from 0, power transfer rises, peaking at 90. Beyond that, further increases in delta reduce the power transferred. When a fault occurs on the transmission line, the effective reactance increases due to an additional shunt reactance XF introduced at the fault point. Different types of faults, such as single line to ground, line to line, or three-phase faults affect this equivalent reactance differently. For instance, single line to ground faults have a smaller impact on the system's reactance, while three-phase faults can completely block power flow between generators. Following a transient fault, the system is typically returned to service after a controlled trip and reclosure, with the power angle curve shifting to reflect the pre-fault, fault, and post-fault operating states. This detailed understanding of power system behavior under various disturbances underscores the importance of using precision protection schemes like OST and OSB to maintain stability and reliability in modern electric grids. The power angle curve is a fundamental tool for visualizing and understanding generator behavior. It plots the active power delivered by a generator against the load angle, the phase difference between the generator's internal voltage and the terminal voltage or that of the grid. Key aspects include sinusoidal nature, as the angle increases from 0 degrees to 90 degrees, power transferred rises reaching its maximum at about 90 degrees. Stability limits, beyond 90 degrees, a further increase in the load angle reduces power transfer, and if the angle exceeds a certain threshold often approximated as 120 degrees in some studies the system reaction becomes unstable. Dynamic behavior, during a disturbance, the machine's rotor angle shifts along this curve. Tracking this movement helps determine whether a power swing is transient and stabilizing or heading toward instability loss of synchronism. Transmission impedance during a fault. During normal operation, the impedance seen at a generator's terminal reflects the line parameters. When a fault occurs, a shunt or additional impedance depending on fault type is introduced, causing a sudden, almost instantaneous shift in the apparent impedance. Fault versus swing. Fault conditions typically produce a rapid step change in the impedance due to the near instantaneous fault current than the slower impedance change caused by a power swing. Relay calculations. Distance relays rely on these impedance measurements. They must distinguish between a genuine fault, a step change, and a power swing where the impedance changes gradually over several cycles. Transiently stable and unstable systems. After a large disturbance, the system can be transiently stable if the rotor angles oscillate within bounds and eventually settle into a new equilibrium, or transiently unstable if the oscillations grow. Critical clearing angle delta C. There exists a boundary angle beyond which the system cannot recover. If the rotor angle exceeds this critical clearing angle, the disturbances become self-reinforcing, eventually leading to generator separation and potential cascading outages. Time frame. Transient stability analysis is typically concerned with the first few seconds after a disturbance, as this period is crucial for deciding the corrective protective actions. Loss of synchronism characteristic. The loss of synchronism or out-of-step condition happens when a generator's rotor angle drifts significantly relative to the rest of the system. Consequences. Excessive angular separation can cause high peak currents, mechanical stresses e.g., pulsating torques and winding stresses, and potential equipment damage. Need for isolation. Once the machine's excitation angle goes past a critical threshold, it becomes imperative to separate or island the affected part of the grid to preserve the integrity of the remaining network. Impedance measured. By distance relays during OS, distance protection relays perform impedance calculations by measuring the voltages and currents at the relay location. Variation under OS. During power swings, these apparent impedance values continuously vary because of the shifting phase angles and voltage magnitudes. False trips. Without proper mitigation, these relays might mistake a benign power swing for a fault condition, potentially leading to undesired tripping. Calibration challenge. The inherent difference between a fault-induced step change and a gradual swing in impedance requires careful calibration and adaptive logic in the relay settings. Effective OOS condition on transmission line relays and relay systems. During an OOS event, the dynamic behavior of voltage and current can adversely affect the performance of protective relays. Relay sensitivity. Traditional distance relays might see the impedance excursion during a power swing as a fault, causing them to operate inappropriately. Blocking functions. To prevent this, many modern systems incorporate protective features such as power swing blocking (PSB) that block relay operation during stable swinging conditions. Overall system impact. Such measures ensure that only when the system becomes truly unstable, i.e., out of step with dangerous oscillation levels, will corrective actions be triggered. Out-of-step protection philosophy. The philosophy of OOS protection is twofold. Avoid unwanted trips. It aims to prevent protection schemes, especially distance relays, from tripping during normal, damped power swings. Isolate unstable areas. At the same time, it ensures that if a genuine loss of synchronism occurs, the affected generators are promptly disconnected to protect both the equipment and the overall system stability. Strategic separation. This controlled islanding helps maintain balance in the remaining grid, preventing widespread blackouts and equipment damage. Out-of-step detection methods and types of schemes. Detecting an OOS condition involves differentiating between stable power swings and true loss of synchronism. Methods include impedance rate of change methods. The most conventional approach monitors how quickly the apparent impedance changes. A fast rate is typically indicative of a fault, while a slower, sinusoidal variation corresponds to a power swing. Graphical techniques. Some schemes use the trajectory of the impedance locus using shapes like double blinders, concentric polygons, etc. to distinguish conditions. Wide area measurements. Modern systems may incorporate phasor measurement units (PMUs) to leverage wide area data and predictive algorithms, sometimes aided by machine learning, to detect subtle patterns. Setting free or adaptive schemes, newer techniques aim to minimize user-dependent settings by automatically adapting to system conditions, thereby increasing reliability. Out-of-step protection is generally divided into two primary functions. Out-of-step tripping, this function is tasked with actively disconnecting generators or parts of the network that have lost synchronism. OST relays are critical for isolating unstable areas quickly to prevent the spread of disturbances. Out-of-step blocking, here, the goal is to prevent tripping of relays that might misinterpret stable power swings as faults. OSB functions ensure that protective devices remain inert during conditions that are merely oscillatory rather than truly unstable. Out-of-step tripping and blocking functions application and coordination. The practical application of OST and OSB functions involves pre-selected disconnect points. System operators determine strategic network locations where controlled isolation can minimize damage. Complementary operation. OST is activated in cases where the generator's swing exceeds stability margins. In parallel, OSB functions block actions by relay elements that could trigger unintended separations in other parts of the network. Dynamic settings, because system conditions like load, system configuration, and even renewable penetration can change, these functions are often dynamically tuned based on transient stability studies and relay simulation results. Improved coordination. The integration of these functions with distance protection enables the system to detect and clear actual faults promptly even during an ongoing power swing by temporarily unlocking blocked relays under fault conditions. Distance protection for faults during system out-of-step. Even while a system is in a power swing or an incipient loss of synchronism state, faults e.g., short circuits may occur. Designing distance protection for this scenario requires careful consideration. Correct fault detection. The relay logic must differentiate between the impedance variations caused by a fault and those stemming from a power swing. Unblocking mechanisms. In some schemes, distance relay elements are initially blocked during power swings via OSB. But if a fault is detected characterized by abrupt changes in impedance or voltage current parameters, the circuit unblocks the relay to clear the fault. Protection coordination. This dual-mode operation ensures that while the system benefits from power swing stability, genuine faults are not missed, thus preserving system integrity even under adverse dynamic conditions. Together, these concepts form a comprehensive framework for maintaining grid stability and reliability. Out-of-step protection systems are a critical part of modern power system operation. They detect nuanced differences between benign oscillations and hazardous instability, and they coordinate protective actions through OST and OSB functions to isolate disturbances in a controlled manner. Furthermore, the integration of advanced detection algorithms and dynamic relay settings enhances distance protection performance during complex system conditions, including the challenges posed by intermittent generation sources and rapidly changing load profiles. This detailed explanation touches on both the fundamental theory like the power angle curve and transmission impedance during faults and the practical innovations adaptive tripping and blocking, PMU integration that have advanced modern power system protection. Implementing out-of-step and out-of-step blocking functions in a large power system is challenging due to the inherent complexity and varying operating conditions. Although the basic philosophy is simple, selecting optimal network locations for these systems requires extensive transient stability studies. These studies reveal constraints on angular stability, identify generators prone to losing synchronism, and map out the swing loci, that is, the paths of voltage current variations during disturbances. The recommended approach involves several key steps: stability and location analysis. Transient stability studies help determine system constraints and identify areas and generator groups that are susceptible to out-of-step conditions. These studies also pinpoint optimal locations for OST-OSB protection based on the behavior of the apparent impedance, which is influenced by MW and MVAR flows in transmission lines. Determining swing loci and separation points. The optimal detection point for an out-of-step condition is near the system's electrical center, where impedance variations can be effectively monitored. It is also crucial to locate suitable separation points islanding based on impedance between areas, load generation balance, and the ability to maintain stable post-separation areas. Setting protection parameters. The OST-OSB schemes rely on monitoring the rate of change of impedance. Settings are established by determining the maximum rate of slip from angular change versus time studies and then configuring two impedance boundaries, an inner zone and an outer zone. The inner zone is set to cover the overreaching zone of the phase distance element, while the outer zone is positioned outside the anticipated load impedance locus to avoid false trips. Relay logic and timing. Two timers are involved, one for detecting blocking conditions OSBD and another for tripping conditions OSTD. The system can be configured to trip on the way in tow or on the way out tow, with tow being more common since it activates when the voltage sources are nearly in phase, reducing stress on breakers. Special care is needed when considering tow because tripping while near an out-of-phase condition can risk equipment damage. Modeling and fine-tuning. Mathematical models of the OST and OSB detection and operation help finalize relay settings and ensure that the protection schemes operate reliably under the fastest anticipated swing frequencies and various load conditions. This systematic approach aims to minimize undesirable relay operations, prevent equipment damage, and achieve controlled system separation during out-of-step events.